Okay, let's talk about steel. Ever wonder how it gets that legendary strength? Well, it's all down to what seems like an impossible magic trick happening at the atomic level. So today, we're going to play detective and uncover the secrets behind steel's incredible shape-shifting abilities. All right, so here's where the mystery really kicks off. You take a perfectly polished piece of steel, and when it transforms, its surface does something, well, something that should be totally impossible. It creates this perfectly flat, shear-like tilt. It's almost as if all the atoms just decided to move in perfect unison. But how? How can billions and billions of atoms rearrange themselves that perfectly? That's the puzzle we're digging into.
So let's really break this paradox down. On the surface, what we see looks super neat and tidy. You can see how a scratch on the steel gets deflected but stays perfectly continuous. It looks like a simple, clean shear. But underneath that calm surface, it's absolute chaos. We're talking billions of atoms just violently rearranging themselves into a whole new crystal structure. So the big question is, how does this atomic mosh pit create such a perfectly ordered, perfectly flat surface? That's the heart of the mystery.
Okay, so to solve this, scientists had to go right to the source. They had to examine the evidence from the crime scene itself, the surface of the steel. So they get out these incredibly powerful microscopes to get a closer look. And what they find is that the boundary, the interface between the old crystal and the new one, is perfectly seamless. Imagine two totally different Lego structures fitting together without any gaps, no misalignments at all. That's what's happening. The fancy term for this is invariant plane strain, which basically just means that one single plane of atoms remains completely untouched and undistorted during this whole chaotic transformation. And that just makes the mystery even deeper, right? I mean, how do you completely rebuild a building but leave one single floor perfectly intact? Right, so we've got the evidence. Now, the scientists needed a suspect. They needed a theory for how these atoms could possibly be rearranging themselves to create this bizarre effect. And the first and honestly most logical explanation came way back in 1924 from a scientist named Bain. He came up with a really simple model. He said, look, you just take the original cubic arrangement of atoms, you compress it along one direction, and you expand it along the other two. It's a really intuitive squeeze and stretch. Makes a lot of sense. And this is a fantastic way to visualize the problem. If you think of that original arrangement of atoms as a perfect sphere, the Bain strain just squishes and stretches it into an ellipsoid, like a football. This simple visual is absolutely key to understanding why this theory, as logical as it seems, just doesn't work. And here's where it all falls apart. An ellipsoid, just by its very shape, doesn't have a single perfectly flat, undistorted plane on it. Every single point on its surface has been stretched or squashed in some way. And that directly contradicts our number one piece of evidence, that perfectly unchanged, perfectly flat interface plane we see in the real world. So the Bain strain, as elegant as it is, just doesn't fit the facts. We need a new suspect. So our first suspect? Busted. It's got a rock-solid alibi. But decades later, a new theory comes along. And this one didn't just solve one little part of the puzzle. It solved everything all at once. Now, before we get to the big breakthrough, scientists did try to salvage the Bain model. They figured out that if they just added a simple twist, a rotation, to that squeeze and stretch, they could perfectly explain the weird angle between the old and new crystals. And that was a huge clue, but it wasn't the whole story. It's like they found one piece of a massive jigsaw puzzle, but the rest was still a total mess. See, they could now explain how a single line of atoms could line up perfectly, but they still couldn't explain the entire plane. The main mystery was still unsolved. And then, in 1953, the answer finally arrived. And it came from two independent teams at the same time. It's called the Crystallographic Theory of Martensite. And let me tell you, this thing was so powerful, so predictive, it's still one of the cornerstones of metallurgy today. Get this, it made predictions about the internal structure of steel that scientists couldn't even prove were true until microscopes got powerful enough years later. That's how good it was. So, what was the big secret? Well, it turns out it's not one magic trick, it's two happening at the exact same time. It's kind of like a dance. You've got the first move, the shape shear, which creates that perfect shape we see on the surface, but oops, it puts all the atoms in the wrong spots inside. Then you have the second move, the internal shear, which goes in and fixes the positions of all the atoms. But if it did that by itself, it would totally mess up the overall shape. But, and here's the genius part,
When these two shears happen together in these fine alternating layers, they basically cancel out each other's mistakes. The result is a perfect shape on the outside and a perfect atomic structure on the inside. It's just an incredibly elegant solution. And bam! Just like that, every single piece of evidence just clicks into place. This one theory perfectly explains everything. The perfect surface shape, that strange, irrational angle between the crystals, that bizarre interface plane, and it even predicted those fine, layered structures inside the martensite that were later confirmed with electron microscopes. The mystery was solved. Case closed. Now, to really appreciate just how brilliant this two-shear solution is, it actually helps to look at a much simpler case. See, in some types of steel, the transformation is way more straightforward, and it really highlights why that complex solution was necessary for our main mystery. So, in some other iron alloys, the transformation is a lot simpler. The original atoms are stacked in layers, kind of like a deck of cards, in this repeating ABC pattern. All the transformation does is just shuffle those layers into a simpler AB-AB pattern. That's it. And because that change is just a simple slip of atomic layers, it can be done with just one single clean shear. There's no paradox, no mystery here at all. And in this case, the interface is a nice, simple, rational crystal plane. And this is great because it proves the whole underlying concept, right? When a transformation can be done with a simple shear, nature does it. It's only in our more complex case that nature had to come up with that incredibly clever two-shear solution. Okay, so this is a really fascinating scientific puzzle, but you might be asking, why does a theory from 1953 matter so much today? Well, it's because understanding the how is what allows us to actually design the future. And this is where all that detective work really pays off. Because we finally understand how this transformation works, we can basically become architects of steel. We can carefully control the process, for example, by rolling the steel to create these tiny flattened pancakes of grains, and we can literally tell the martensite exactly how to form. This gives us the power to fine-tune the final structure of the steel and create materials with properties that honestly sounded like science fiction just a few years ago. This level of control has led to the creation of these new super steels that can withstand a mind-boggling 2 gigapascals of stress. Now, to put that into perspective, that is like stacking 3 entire statues of liberty on top of a single postage stamp. I mean, that is an incredible amount of strength, and it's all because we finally understand this intricate atomic-level dance. But here's what's truly revolutionary. All that strength doesn't come at the cost of making the steel brittle. No way. These new steels maintain amazing toughness even at freezing temperatures, like -40 degrees Celsius, a temperature where most conventional strong steels would just shatter like glass. So, this new understanding just completely rewrites the rules. That old story you learn in school, that martensite is super strong but not tough, it's just not the whole picture anymore. This proves that by engineering the transformation at the atomic level, you can design a material that is both supremely strong and exceptionally tough. Solving this decades-old mystery has literally unlocked a whole new generation of supersteels. And it really leaves you wondering, doesn't it? What other profound physical principles, what other elegant solutions are hiding in plain sight, just waiting for us to discover them in the everyday materials all around us?